unit is on two topics. One of them is on polynomial functions, and then we're also going to look at function operations, like what happens if we add functions or subtract functions or multiply or divide functions, that sort of thing. Okay, and a lot of the functions that we're going to look at with those function operations will be polynomial functions. Okay, this is, I would say, in general, one of the units that people find a bit easier, which hopefully will be good news for you. But yeah, we've done some of the harder stuff already. So anyway, let's get into it. Okay, polynomial function. What is a polynomial function? What's a polynomial? What's that? Numbers and letters, yes. Right, let's actually look at some examples of polynomial functions first, and then maybe we can work towards a definition. What would be an example of a polynomial function? Polynomials like numbers and letters together. So what would a polynomial function be? Give you a hint, linear functions and quadratic functions are polynomial functions. Yeah, well, that's a polynomial. Polynomial function would be y equals 2x plus 5. Okay, another one. Y equals 2x minus 5. Okay, let's get something more interesting. Those are both linear. Sure. Y equals 2x squared, and then what was it? Minus 8 or something? Plus 5. Okay, well, I'm turning it into minus 8. Okay? So this is linear and quadratic. So we've spent quite a bit of time looking at those two types of functions. But you could have something like this. Whoops, not y squared. Y equals 3x cubed minus 2x plus 4. That is a polynomial function, and it's specifically a cubic function. Okay, you could have y equals 21x to the 50 minus 2x to the 31 plus x minus 4. Okay, because y is given as a polynomial in terms of x. Okay, polynomial is essentially the sum of powers, the sum, I suppose, of the product of power of numbers and variables. Okay, so a function that relates y to a polynomial, and a polynomial is the sum of products of numbers and variables. And or variables, right? So for example, if you even just look at this term, we're multiplying 21 by 50 x's, x, 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 all the way to 50 of them, right? So that's a product of a number 21 and x multiplied by itself 50 times. And then we're adding or subtracting. I think about sum in general because you can think of a sum as adding a negative number if it happens to be negative, of negative 2 times x multiplied by itself 31 times, right? So that's essentially the definition of a polynomial. Non-examples. The key, I suppose, is that if you look at the position of the variable is sort of in the base of the power. Okay, and then there may be a coefficient, a number attached to it. Okay, what would some non-examples be?
Y is equal to 2 to the x minus 4.
Yes. Okay, the variable here is in a different position. It's in the position of the exponent, so this would be an exponential function. Okay, or if you think about on any of the other types of functions we've looked at, yeah?
Y equals 1 over that.
Yes. 1 over x. Okay, this is a rational function. And even though you can write it as x to the negative 1, we're not multiplying by x in this case, we're actually dividing by x. Okay, so anything rational where there's a variable in the denominator is not a polynomial function. Okay, yep? Okay, good question. Yeah, this is not either. X to the half or the square root of x. This is a radical function. Yeah. And the reason why we classify functions in these ways is that if we look at these various families of functions, polynomial functions, exponential functions, rational functions, radical functions, we can make generalizations about the way that they behave, right? So for example, like what is the domain and range of these things? Is there an endpoint? Are there any values where the function might be undefined? And we can make generalizations about that, okay? This would be another one. Something like that, an absolute. Even if you're taking the absolute value of a polynomial, that is not a polynomial function. Yes?
But like Nick said, it could just be x to the half, so why is it not?
This guy?
Yeah.
Okay, because we're not actually multiplying a number and a variable there, right? It's not the variable itself, it's the square root of the variable. Yeah. Okay. All right, there's lots of other examples, or non-examples specifically, but let's just leave it at that for now. Some others that we'll explore in this course, actually, something like this. You haven't looked at this yet, but this would be a trigonometric function. We looked at logarithmic functions. Okay, that kind of thing. So being able to classify a function, put it into a category, can kind of compartmentalize in your mind trends that happen in those types of functions. Okay, so within a polynomial function, some of the things that we want to be looking at are these things, specifically these three. What is the leading coefficient of the function? What is the degree of the function? And what's the constant value? Because ultimately what we want to do is be able to take an equation, connect it to a graph, right? Or be able to visualize the graph, and then make certain statements about that function, like domain and range, end behavior is 1, that kind of thing, okay? So let's look at some of these examples that we have here. What is the leading coefficient of this function? 2. What about this one? 2. Yep. 21. 3. Okay. What if I had something like this? Y equals 1 minus x squared. What would the leading coefficient be there? -1. Yes. So the leading coefficient is the coefficient of the term with the highest degree. Okay? The degree? What's the degree of this guy? 2. This one? 1. This one? 2. What about this one? 3. Yes. Okay. So it's essentially the highest exponent on x that appears in the function. Okay? Okay? Now in reality, in fact, the degree is the highest sum of exponents that you see in a term. But in this course, we're not really going to see polynomial functions in 3 variables. So for example, let's say you had the term a squared b cubed. The degree of that would be 5, because the degree is essentially counting how many variables you're multiplying together. And you're multiplying 2 a's and 3 b's. So all together, that's the product of 5 variables. Okay? But honestly, in this course, we're really just going to see polynomial functions y in terms of x. Or, you know, if it's a context, we might see distance in terms of time, or that kind of thing, right? But there's only going to be 2 variables. Okay, constant. What's the constant? Yeah.
Isn't it the number without a variable?
Correct. It's the number that's not attached to a variable. So for example, what would the constant be here? -4. Yeah. Okay, this would be -8. If you just have like y equals x, then the constant is 0. Okay. End behavior. Okay, so we can talk about end behavior for any function, actually. But, yeah?
Sorry, is it just like domains and ranges?
So we're going to look at all of those things, but end behavior specifically is a description of the function, the y values, as x goes from -infinity to infinity.
Is it
Yeah.
like the thing like as x approaches 0, y approaches -1?
Exactly, but specifically, so we looked at that sort of thing in rational functions when x approaches a finite value because that was the non-permissible value. But end behavior, like a really short way of saying it, is it's a description of the graph from left to right. Okay, now this is sort of layman's terms. Specifically, we're asking how is y behaving as x goes from -infinity to infinity. Or, I mean, that's a very big generalization because if you're looking, for example, at this function, y equals the square root of x, then the function's not defined at -infinity. So if there's an endpoint in there, you'd start at that endpoint. Okay? Now, one of the easiest ways of describing end behavior is to talk about the quadrants of the coordinate plane. Okay? So for example, if I'm looking at this function, okay, quad 1, 2, 3, 4. From left to right, the y values start in quadrant 2 and go down to quadrant 4. Okay? And that's what would happen at the extremes. When x is at -infinity, this will still be in quadrant 2. So it doesn't matter if there's some hiccups along the way and it crosses into quadrant 1 for a little bit. The end behavior here is Q2 to Q4. Okay? Another sort of common, how would I put this, characteristic that we would attach to polynomial functions specifically is we might talk about whether they're increasing or decreasing. Because a polynomial function is defined for all values of x. So the domain is from -infinity to infinity. So at the end of the day, is it going to increase and end up in quadrant 1, or is it going to decrease and end up in quadrant 4? So that's another descriptor that we might talk about. Is the function increasing or decreasing? Okay. Okay, so I want to look at these various functions and then decide as to whether or not these functions are polynomial or not. And there are a couple of like trick questions in here. Oh, actually, before I talk about that, I want to talk about one more thing up here. Okay, another description that we can give to polynomial functions is we can talk about whether they're even functions or odd functions. Okay, so what do you think that might refer to? Let's take a look at some of these. So we've got a bunch of different functions up here. I'll give you a hint. It's connected to the degree. Okay, so yeah?
If the degree is even.
Yeah. Yeah. So functions that have an even degree are going to behave in a certain way, and functions that have an odd degree will also behave in a certain way. So that's another thing that we're going to pay attention to, specifically with respect to end behavior. Okay? Okay? All right, so let's take a look at some of these functions. So firstly, there's a couple here that I can just cross off. Is there anything here that you can, like, cross out? Yeah.
Say B for sure.
Yeah, B for sure, right? This is not, because, right? We're essentially dividing by x. We're not multiplying by x there. What about, what else? D, yeah, this is a radical function. Okay, so that's not. Okay. What about these two? Yeah.
I think A would be.
Yeah. This is really tricky, but A is a polynomial function, because if you take the square root of x squared, that's equal to x. Okay? So that one's kind of tricky. Okay? Essentially, this would be f of x equals 5x to the 4 minus root 3x minus 4x plus 1. Okay? So the fact that the coefficient is a radical is fine. The degree, rather, on x here is still 1. So this is. Okay, what about this guy? F of x equals the absolute value of x squared minus 2x to the 5 plus 4. What do you think? Yeah. Okay, so this one is really tricky. With absolute value, it kind of depends. Yeah.
Does it not, or the x in that case couldn't be a negative number because it's squared? Does that have something to do with it?
Okay, so think about, when you think of absolute value, okay, essentially to graph this, you could look at, or even just this. Let's do this instead. This is better. Absolute value of x minus 3. Okay? In fact, I'm not even going to do that. I'm going to do this. This is what happens when I improvise. Change my mind all the time. Okay, let's look at the graph of y equals absolute value of x. Okay? To get an absolute value function, you can look at the function without the absolute value symbol around it. So think about y equals x. Okay? And then the absolute value signs make it positive. So this is already positive. Nothing has to change there. This is going to get reflected up. This has to get reflected over the x-axis. Okay? Consider this. What if you had y equals the absolute value of x squared? Yeah? Okay, so if we graph y equals x squared, I'll do that in red. Yeah, it's the same. So in fact, in this specific case, that term, 3x squared, is equal to the absolute value of 3x squared for all values of x. So in this specific case, this is polynomial. However, we can't generalize that for all polynomial functions. Yeah. Or for all absolute values.
Can you write an example of the same thing?
Yeah. Okay, so so a couple things you need to look for. Number one, if you're looking at anything with an odd degree, that will not be the same. Because just like here, the absolute value of x is not the same as x. If you think about x cubed, same thing, right? Absolute value of -1 all cubed is 1.
Yeah.
So, you know, if the degree of the term is odd, that will not be the case.
So if the absolute value is on the 2x5.
Correct.
Not
Correct. Yes. And then also, I mean, look, we're really, really, really getting into the weeds here. But if you had something like this, y equals, if the term with the square in it is not isolated, okay, so now it's not just x squared, but x squared minus 4. If you think of the function x squared minus 4, it looks like that. So the absolute value is going to be different because there are parts that are negative. This will be the same, but then this goes zoop. Right? So that term has to be isolated. One thing that you can do, though, is graph both and see if they overlap. Right? But I honestly, like I said, we're getting into the weeds a little bit because we're not really going to come across this that much. We're not going to throw these types of trick questions at you that much. But I think it's an interesting conversation to see, like, when does it matter to have these absolute value signs? When is it going to make a difference? Or when does it matter to have a radical or not, right? So yeah, these two are kind of tricky. These two are. This one is as well. And that's since 3x squared is equal to the absolute value of 3x squared for all values of x. Okay? This is always going to be positive or 0. So putting absolute value signs around it isn't going to change its value. Okay. So what I have here is a bunch of different functions that have been graphed for you. They are all polynomial functions. So if you look at the top line, these ones are all quadratics. They look like parabolas. Okay? And then in the bottom row, we've got some quartic functions. So a quartic function is something that's degree 4. And you can see actually that the shape of the graph can vary. So if you just have f of x equals x to the 4 with no other terms, it kind of looks like a U shape, like a wide parabola. Okay, and here, same thing, but it's been reflected down. Here we've got other terms, and so there's a couple of like bumps along the way. Okay, but what I want you to think about here is these are all even. I want you to consider the end behavior and see if we can make a generalization about even functions and end behavior. Yeah.
They all seem to go like up and down, I guess, right?
Yeah. So, I mean, if we specifically talk about quadrants, like this starts in 2 and ends in 1, starts in 3 and ends in 4, starts in 2, ends in 1. So, I mean, we can't really make a generalization yet about that, but they seem to kind of start and end in the same direction in terms of the y values. Okay? So if they start and end in the same direction, one thing that's also going to result from that is that you're going to have a minimum value or a maximum value. They're not going like this. They're going like this or like this. Okay? So one thing that we can say is that they start and end in the same direction. Okay, either up or down. Now let's see if we can figure out what's going to predict the up and down piece. So the ones that start up and end up are this one, this one, this one, this one. Okay. So what do those have in common? Yeah. They all have a positive A value. Okay? The A value for all of them is 1, but the important piece is that it's positive. Okay? So if the term with the highest degree has a positive leading coefficient, those functions at the end of the day are going to increase because we're taking a positive value, let's say 1 or 2 or whatever, and multiplying it by infinity by some power of x, that's going to end up being positive. Okay? So if they end up, we have a positive leading coefficient. And then conversely, if they end down, we're taking a negative value. Think about the direction towards infinity, right? Say x is 100 or 1,000 or whatever. If you take a negative value, -2, and multiply that by 100 or 1,000 or infinity multiple times, the overall answer is going to be negative. Okay? Now, if it ends up, yeah, it's going, 2 to 1. Ooh, that's a little thick, right? The end behavior is 2 to 1. If it ends down, that end behavior is 3 to 4. Okay? And this would, I haven't put these down for you, but if we looked at some degree 6 polynomials or degree 10 polynomials or degree, 72 polynomials, as long as it's even, we're going to see the same sort of pattern. Okay, so now let's look at some odd functions. So the first 2 functions are linear, degree 1. Then we have some cubic functions, degree 3. These are also degree 3. This is a degree 5 function, and then this is also a degree 5 function. Okay, so specifically with the cubic functions and with these degree 5 functions, like here it seems to go, it starts down and then it kind of levels off and then goes up. And here it starts up, levels off, goes down. That's actually called, does anyone know what that point is called? It's called an inflection point, where it kind of inflects and goes the other way. Not important at this stage, but we'll talk about it next semester if you take more math next semester. These ones have some sort of bumps along the way, right? So with the end behavior, we're concerned about the ends. We don't really care about the bumps along the way for now. Okay, so we can still make the same generalization around the end behavior, even if there's different stuff happening in the middle. Okay. And by the way, these ones also have inflection points, but they're just there or there. Okay. All right, so let's talk about end behavior. What can we say about the end behavior of these functions? Yeah? An inflection point, I opened up a can of worms, didn't I? An inflection point is where there's a change in concavity. So a concavity is like a parabola facing up is concave up. A parabola facing down is concave down, right? So if you think about this point right here, the left of it is kind of like a parabola going down. So that's concave down. Here it changes to going concave up. Yeah. Okay. Okay, so let's get back to the generalizations. What can we say about, in general, start and end of these types of functions? Yeah? Yeah, they start and end in opposite directions. So if it starts down, it ends up. If it starts up, it ends down. Okay. Now, if you think about y equals x cubed, you know, the reason why we see this is that if you take a negative number and cube it, you're going to get a bigger negative number, right? Whereas if we take, you know, the quadratic situation, if we take a negative number and square it, we get a positive number. Okay? So on the left, towards negative infinity, x is negative. Towards positive infinity, x is positive. If we multiply a negative number by itself an odd number of times, we're going to get a negative value. But if we multiply a positive number by itself an odd number of times, it's still positive. So that's why we see this, you know, starting and ending in opposite directions. Okay. What about the leading coefficient? How does that play in? Yeah.
It's positive, then it would go left, right.
If the leading coefficient's positive, where does it start and where does it end?
So we start in, what's that? That's 3 to
3,
1.
yeah. And if the leading coefficient is negative, it starts in 2 and goes to 4. Okay. Now, one thing that is similar between the even and the odd is that they always end in the same place. So if the leading coefficient is positive, it's going to end up. It's going to be an increasing function. If the leading coefficient's negative, it's going to end down in the 4th quadrant, and it'll be decreasing. Okay? All right, so in general, a couple things that I want to track. Okay, so let me think. How do I want to do this? Okay. Even function. And then same thing for odd. Okay. An even function with a positive leading coefficient, the end behavior is going to be 2 to 1. Okay, so it could look like this. It could look like this. Polynomial functions tend to be sort of smooth and hilly. Sometimes they have hills, sometimes they don't. But here we're really just tracking the end behavior. Ultimately, it's Q2 to 1. Okay. If the leading coefficient is negative, it's going to be reflected down. Okay, so the end behavior will be 3 to 4. So it might look like, could even be really hilly in the middle. That's even. Or, I mean, we can just have a quadratic function too. Okay, so this is Q3 to Q4. And then if it's an odd function, starts and ends in opposite directions. So for positive leading coefficient, if it's linear, think about the linear function, right? The easiest way to remember this if you're struggling is think about what y equals x looks like, y equals negative x, y equals x squared, and y equals negative x squared. If you can think of those four functions, the trends just follow. Okay? So this could be a linear function. You could have that would be cubic. Okay? But at the end of the day, starts in 3, ends in 1. So the end behavior is quadrant 3 to quadrant 1. Okay, and then finally, an odd function. Think about y equals negative x, right? 2 to 4. Or you could think of y equals negative x cubed. But yeah, if you're trying to just get a really small snapshot, y equals x, y equals negative x, that's the odd positive negative. Y equals x squared, y equals negative x squared. Parabola opening up, parabola opening down. And then you've got the even ones. Okay, so we could also have that. That's also odd. Okay, so this one goes Q4. No, Q2 to 4. You start left to right. Yes. Okay. So there are a number of ways that we classify polynomials. Okay. And we've already looked at some of them. Okay. So the first thing that we could look at, and this is not really something that we've looked at today because you looked at it in grade 10 and 11 a little bit, is we can classify them by degree, right? A linear function is going to look different than a quadratic function, which is going to look different than a cubic function. Right? So degree is one thing that we can use, right? So degree 1 is linear. Quadratic, cubic, etc. Okay, now after degree 4, quartic, they don't really have special names. I think there's also a quintic, which is degree 5. But in reality, like if you think about functions and why we have them, they're to model things in real life. Okay, now in the field, we don't really see much beyond degree 3 a lot because the world exists in 3 dimensions. So a linear function might represent length. A quadratic function could represent area. A cubic function could represent volume, for example. Okay? There are instances where we see, and we're going to look at them in this course just to get an understanding of these types of functions and make generalizations. But, those are the 3 most common ones that we see in the field in an application sense. Okay? We can classify them by whether or not they're even or odd. If they have an even degree or an odd degree. And we've already seen that in terms of the end behavior, there's some generalizations that we can make there. We can classify them by the sign of the leading coefficient. Right? And I suppose I'll elaborate a little bit. In terms of the even-odd piece, that really affects the end behavior, right? And whether or not the function will start and end in the same direction or start or end in different directions. The sign of the leading coefficient also affects the end behavior, but also it's an indication as to whether the function will increase or decrease. Because whenever the leading coefficient is positive, it ends in quadrant 1, it's increasing. Whenever it's negative, it ends in quadrant 4. Yes?
What's the difference when you say even or odd or sign of leading coefficient? What's the difference between those two? So isn't the sign of coefficient, doesn't that
So the sign of the leading coefficient is the sign of the number in front of the highest degree, right? The whether it's even or odd is the degree of the function even or odd? Yeah. Okay, so this also affects the end behavior. But it also tells us whether the function is going to increase or decrease. Okay. Now, one other thing that I want to talk about that I sort of forgot about for the even thing, I think I sort of mentioned it briefly, but I just want to go back to this picture again. Because I spoke about the fact that for these polynomials, the domain for all of them is x is an element of the reals. These are defined, if you're looking at multiplying values of a variable together, you can put whatever you want in there, and it's going to be defined. Okay? One thing I do want to talk about, though, is the range. So let's start with these first. If they start up and end down, or start down and end up, what would the range of these odd functions be? Starting and ending in opposite directions. Yep.
Like Y-E-R?
Yeah, y can be anything. If they start and end in opposite directions, the range is y is an element of the real numbers. Whereas with the even functions, if they start and end in the same direction, if they both start up, there's going to be some minimum value of that function. And similarly, if they both start down, there'll be a maximum value. And again, if you can picture y equals x squared and y equals negative x squared, then it gives you an idea of how that, those generalizations that you can make about even and odd. Okay? So that's another piece that I just want to mention here is that there will always be is always a min or max value. Okay? Okay, so one other thing before we get into the next question is when you look at a function that's a polynomial function, there are two types of min and max points. Okay? There is an absolute maximum or an absolute minimum, which is the absolute smallest or biggest that the function could be. So for example, in this function over here, this point over here is the absolute min. That's the lowest that it goes. But when you get these bumps along the way, we can also talk about something called a local minimum or a local maximum. And a local minimum or local maximum is essentially locally, close to the point. What's the maximum value? So, for example, this is a local maximum, and this is a local minimum. Okay, this is a local max. And this guy is a local min. It's kind of like saying, I don't know, who's the richest person in the world? It's not Bill Gates anymore, but whatever. Let's say it's Bill Gates, right? Versus the richest person in Calgary. Locally, this is the richest person. Globally, Bill Gates is the richest person, or he used to be anyway. Okay, same sort of idea. Okay? So when we do this next question, we are going to keep that in mind. Okay? So describe the end behavior of the graph of the function f of x equals negative x cubed minus 3x squared plus 2x plus 1. Okay? So let's start with that. Describe the end behavior. Okay, so what is the degree of this function? 3. So that would be an odd function. Okay, so So what do we know about that? It's going to start and end in opposite directions. Now this, sorry, I didn't read through the whole question, but this is a matching question. Okay, so far we can't rule anything out because all of these start and end in opposite directions. Okay, what about the leading coefficient? Yes. So if the leading coefficient is -1, I always remember if it's negative, it ends down, right? And then depending on the degree, it's going to start or end in the same direction. So it's going to end in quadrant 4. So the end behavior is going to be quadrant 2 to quadrant 4. Okay, so let's see. These two are out. Okay. Now the last piece, and I haven't talked about this yet much, but the last piece that we can use to connect an equation to a graph in a polynomial function is the constant. Okay. Where do you think the constant might show up on the graph? Yeah, it's the y-intercept, because the constant in a polynomial function is the value of the function when x equals 0. Okay, so the constant is the y-intercept. Okay, so, and if you think about it, f of 0 is -0 cubed. I can't even remember the rest of the function. What was it? Minus 3x squared plus 2x plus 1. Minus 3 times 0 squared. Was it plus 2x? Plus 1, right? Doesn't matter what all of these terms are. Anything with an x in it is going to disappear. So all that's left is the constant. So that's the last piece that we can use. We have a positive constant. So this guy is C. This is the one. Okay, now, state the x-intercept, y-intercept, and if the graph has a maximum or minimum. Okay, so this graph, does it have a maximum or minimum, an absolute maximum or minimum? No, so it doesn't have an absolute max or min. But there is a local max and a local min. Okay, now at this point, for this particular function, all we can do is use technology to find the x-intercepts and the local max or mins. So, or if there is an absolute one, we could do that too. Okay, so, you know, and you guys have done this before. It looks actually, when I look at it, oh no, it looks like they're irrational, right? I'm trying to look at the scale. It doesn't look like they're right on the little ticks or whatever. So I'm just going to graph this thing. Clear. And then we can take a look at it that way. So negative x cubed. Shoot, why can I never remember this stuff? Minus 3x squared.
Are you able to like copy paste the equation into the
No. Wouldn't that be nice though? I can't even from my computer type everything, because if I type an x on my computer, it shows up as the alpha x, not the variable x. So I can type like signs and numbers, and that's about it. And then plus 2x plus 1. Okay, so there we go. And, you know, I should have done this on the Casio, because it's so much easier to find these points. But let's find the zeros first. Enter. That's good enough. So there's a 0 at negative 3.49. And then, I don't know what the other ones are. You got to do this all over again. 2. Takes a little bit of time. Enter. 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 0.34.
The other one is at 0.83.
0. Thank you. Okay, so there's the x-intercepts. To find the local max or min, you just find a min here and a max there. Are we okay without doing that as a group? Yeah? Okay, thanks. Okay, so the last thing that I want to do with you guys today might seem kind of random, is I want to review long division. Yes?
Are we going to have a quiz without a calculator?
Or we can have a quiz with what?
Without technology?
No. But we're going to start to divide polynomials, and we're going to do polynomial long division. And it mimics long division. Because do you guys know that a polynomial is just models place value? You know that, right? Because like any number can be written as powers of 10. A polynomial are just powers of x. Have you seen that before? Oh. Yeah, so I don't know. I'm going to go on a slight tangent. Okay, so if you think about the number, I don't know, 3,241, okay? Doesn't that kind of look like a polynomial to you? I'll put a 1 in there.
I mean, if 10 was x, yeah.
Exactly. So, wow. Okay. That was impressive. Okay, yeah, so, no, the reason why I want to bring this up, though, like, yeah, if x was 10, then yeah. But actually, you can work in different number bases, right? Like, computer science uses base 2. There's only 2 digits, 0 and 1. We use base 10, so there's digits 0 to 9. But you could use base 5. I mean, you could. The world is built around base 10, so we don't typically do that. But there is like evidence of different civilizations around the world that emerged using different bases. And do you guys know why the theory is why we use base 10? It's because you're too good at doing mental math. That was the first calculator, people's hands, 10 fingers, 10 toes. Okay. This is kind of relevant though because we can do long division with numbers. And polynomials model numbers. So we can do that with polynomials too. Okay, so here we go. Okay, give me a, I don't know, a 4-digit number. Yeah. Okay, now I want like maybe a number less than 20. 4. Okay. Long division. There's our little long division table. By the way, I once spent a lot of time figuring out why long division works. It was painful. Because long division is the one algorithm in math that I think is actually quite detached from what's happening mathematically in terms of the steps. It always works, but if anyone knows of other ways, any other algorithms to do division, come let me know because I know in different countries this is done in different ways and there's other ways to do it that make more sense. But anyway, let's just go with it. Okay, so where do I start? Okay, does 4 go into 3? No, so I go on to the next one. Does 4 go into 37? How many times? 9. Yeah. Just yeah. There you go. Okay. So then what? 9 times 4. That's 36. So where do I put that? And then we subtract. Yes. So that's 1. Okay. Now what?
You bring the 1 up or bring the 4 down.
Bring the 4 down. Okay, so now this is 14. Okay. Yeah, so how many times does 4 go into 14? Goes in 3 times. And then 3 times 4 is 12. And we subtract. So this is 2. And then bring down the 1. And we get 21.
Five.
Yeah, so that goes in 5 times. 5 times 4 is 20. So when we subtract, we get 1. And there's nothing else to bring down. So this is, what's this called? The remainder, yeah. You got to go all the way back to like grade 3 before you learned about decimals. Okay, so this is the remainder. Okay, so we could say 3,731 divided by 4 equals 935 remainder 1. Or we could say 935 and 1/4. Yeah. Why are we doing it? Just for fun. No. Okay, so what we're actually going to be doing next time we look at this unit is we're going to be doing something called polynomial long division. And it models long division. So I want to review long division first so that we're all clear on how it works. This, honestly, the steps are almost identical. Okay? So, and what we're going to use polynomial long division for is, just to give you a little hint. So take a look at this function. Shh. If this was quadratic instead of cubic, could you tell me, could you algebraically figure out the zeros? You could factor it, you could use the quadratic formula, right? Now, to do something higher than a quadratic expression or function, degree 2, like cubic or quartic, we have to break it down into smaller parts first. And so we're going to use polynomial long division to divide it into factors if possible. In this case, there wouldn't be factors because these are irrational. But we're going to do that so that we can try and figure out, for example, what the zeros are or how to solve a corresponding equation or that type of thing. Okay? All right, so I'm going to leave it there for today.